So in the next 1.5 hours, what we'll try to do is we'll try to basically give you an overview of what OMEC is, what's our goal. We'll go a little bit into the architecture of OMEC, talk about its features, functionalities, performance. Then I also have a demo video that I want to run here so that I can show you how things work at OMEC, what are the different components, how they are initialized, how they communicate, and how to run the test. And then I will hand over to my colleague here, Mikhail, who is also, I think he's also joining remote. And he will take us through the process of feature additions, bug fixes. If you want to contribute to OMEC, what's the process, how exactly things work behind the scenes. And he'll also show us how the continuous integration and the continuous development cycle works for OMEC. All right, so with that, let's get started. So I'll just give you guys a brief overview of what exactly we started with. So what we thought is, okay, so we have the mobile core, the EPC, which is running today in telco networks. And they are typically black boxes or fixed function boxes. What we thought is, okay, why don't we come up with a software implementation of those functions and see if we can have a reference implementation based on those software components, reference implementation of the EPC that can run on just commercial off-the-shelf servers. And we are not expecting these components to be fully compliant and compatible with each and every operator. This is a reference implementation, and the expectation is each and every operator, they will, if they are interested, they will take a look, they will absorb this into their network, make whatever changes they need to make to make it compatible and operational for their situation. Once they do that, we are also expecting them to contribute back their changes back to OMEC so that we have a reference we not only have a reference implementation, but also a conformant and a performant implementation operator wise. So that was our goal. And we also want to make sure that, hey, so these functions are no longer running in a black box, running in a fixed function hardware. They're all running as software processes on top of commercial off-the-shelf hardware. What kind of security can we provide to at least give a certain level of confidence for the telcos that, hey, although these components are running on software, but I still feel comfortable running them because of certain security or certain guarantees that the software components or the technologies underneath the components provide. So that was a very important goal as well. So with that understanding, what we basically did is we open sourced the OMEC project. So as you can see, the URL is there. So that's the URL where you will find all the components that we have open sourced. It's available. By the way, we have open sourced it in February this year. And since then, lot of contributions, lot of changes, lot of pull requests have been accepted, have been merged back. So I would strongly encourage people who are interested in OMEC project, please take a look at the history, take a look at what kind of contributions have been made, what kind of optimizations and changes have been made to the code bases. So once you look into the OMEC project, once you go inside the project with a page, you'll basically see certain repositories. So right now I'm showing the three most active repositories here, C3PO, NGIC-RTC, OpenMME, and then followed by the pre-diameter and deployment and OSS util. So what basically this is, I'll go back to the slide, the earlier slide. So C3PO is basically a, a, a combination of lot of subcomponents in it. So once you go inside the C3PO repository, you will find functions like the CTF, CDF, HSS, PCRF, and also some of the Intel SGX based charge data handling system. NGIC RTC is basically the control plane and data plane, which is the S gateway and P gateway implementation. OpenMME is our implementation of the MME component. And then if you go into the other repositories, free diameter, we have open sourced it, but for at least for our current CI/CD process, we are not using free diameter. IL traffic gen is an interesting traffic generator that we have built ground up here. So you can use it to test the user plane traffic. You can play with the speed, the packets per second, the duration of the test, and number of subscribers, number of UEs. But all these are completely on the data plane. So I would like you to note here that IL traffic gen does not do control plane simulation. It only does data plane simulation. However, having said that, you can also use, if you are using IL traffic gen, you can use the control plane simulation that we have built into our control plane CP and DP, which is the S gateway and P gateway. So with the combination of those, you can do a very decent test. I mean, a test that you can rely on, and you can get some actual performance numbers. Okay, and deployment OSS util, those are mostly for how do you package these VNFs, how do you deploy those VNFs, how do you interact with those VNFs once they're deployed. So I would also encourage you guys to just take a look into those repositories and see how things can work for you. All right, moving to the next slide. So, okay, at the top level, so if you break the GitHub project to components, you will see there are around 13 components that are independent and they are maintained separately. Although some of the components are clubbed together under C3PO, but if you go just counting the components, you will see there are around 13 such components. Basically, the MME, HSS, DB, the S gateway control and U, which is the control and user plane, P gateway control and user plane, CDF and CTF, which are the components for billing and charging, and then we also have the SGX extensions for handling the charging data securely. And I'll go into more details on the SGX part. So looking at the features, by the way, the components were developed in here at Intel Labs with contributions from various telcos, GS Lab, HCL. So all of us, we came together and developed these components. It has gone through Intel's software lifecycle and security development lifecycle processes. That includes the code scans. So when the code was first open source there, it definitely went through the Intel code scans. And now when the code is open sourced, all the components that change, any contribution, any pull request that happens, there is a continuous process where the code scan happens on a periodic basis, and the results are also shown on the website. So at any point of time, you can go and check what the status of the scans are. And if you're an active contributor, you can see what the status of your contribution is, or if there are any red flags in your contribution, that will also be shown. Okay, so what this means is with all these components that I've mentioned on top, basically you get a complete connectivity of the EPC core. You also get a secure billing and charging capabilities. What that means is the charge data records that comes out of the packet gateway, those records are sensitive records, and auditors have problems making sure that those records have not been tampered with. Remember, the telcos have to go through rigorous audit processes to prove that those records are intact. What SGX adds is it gives you a cryptographical, it gives you a way through which you can prove, and it's a cryptographic way. It's not any manual way that telcos they follow today. So it's a cryptographic way to prove that those records have not been tampered with, and that gives that saves a lot of time for the telcos as well as for the auditors. And I'll take you a little bit more into that, how it looks like. So spec-wise, uh, we are 3GPP release 13 compatible, and when I say there's a star there, when I say that we are compatible, I would strongly encourage you guys, before you try to uh, uh, check against the spec, please go and look at the release notes. It's very important. We have release notes where we have specifically called out what exact features are supported and what exact features are not supported. So although we say it's compatible, but there is a caveat. So please make sure you look at the release notes. Again, these are components. They can be individually deployed based on the performance requirements, based on your application. You can scale each and every component based on whatever load you have. And the best thing is our entire contribution process is integrated with an automated CI/CD process. And what happens right from the time you contribute, generate a pull request, you can track the entire life cycle of your request through the CI/CD process. And Michel, who's going to talk after me, he's going to take us through the details and how things look when you submit the pull request. Okay, again, the project is located at GitHub. That's github.com/omec-project. Okay, so with that, let's look how things are connected, how these components are connected. When you want to deploy it, when you want to test it, basically this is the way things will be connected. This is a build slide, so let me quickly switch to the full screen. Can you see my screen? Now I'm on full screen mode. Okay. All right. So traditionally, what we have is we have the S gateway and P gateway connected, as I'm showing in the picture right now. We have other elements like the MME, HSS, the database, the billing, CTF, CDF, and the PCRF functions. They're all connected the way I'm showing here. From the radio access network, you get the control signals into the MME, and the MME talks to various other components and takes actions. Once the control signal process is over, then the data path starts, and the data basically flows through the user plane to its destination and the internet or wherever it needs to reach. Now, when the data is flowing, the packet gateway here is going to generate some records. That means per UE, per session, how much data was used uplink, how much data was used downlink. That kind of information is stored today in a shared storage. So telcos use this model. They store all this information in shared storage, and the billing system on top, which is CTF, the trigger function or the data function, they consume as per their requirement, maybe every 24 hours, maybe every 72 hours, whatever they are programmed for, they will go and look for new records in the shared storage. And based on the data, they will generate the bills and then say to the users. Now, what happens is there is no way that uh, the telcos can prove to the auditors or to the users that, hey, your data, when it was stored in the shared storage, they have not been tampered with. And any malicious telco with malicious intentions, they can go and change whatever they want in those records. For a user who just used 100 megabytes, they can change it to 100 gigabytes. Nothing stops them. And there is basically no way to prove that those records were not tampered with. So the records will look as good as a fresh record. So the problem, so we have a problem. The way we solved it is we used a different type of system based on the Intel's secure guard extensions. What this essentially does is once the data comes from the packet gateway, that channel, right from the point it's generated, so that channel, including the components that deal with the data after it's generated, they are all protected using the Intel SGX technology. What it basically means is from the point the data is generated till the point it's consumed by the CTF on top, there is no way any human being or any malicious application or OS or the kernel or a system can see what the data is, number one. Number two, can tamper with the data or change the way they want. So there is no way. So it provides you confidentiality, and it also provides you integrity. And the third aspect it provides you is protection from replay attacks. That means it's just not someone can go and take a look or change. Uh, 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 Even you cannot change the way it was in a previous state. That means you cannot take an old record and just replay it, showing it as a new record. Even so, it provides you confidentiality, integrity, and as well as protection from replay. And the way it is done is, it's a very elegant way of solving the problem with SGX. Basically, there is a key store, which is also SGX based, which generates a key, and it generates a key inside the SGX environment, which we call enclaves. And once the key is generated inside the enclave, the key is distributed to the billing dealer in, billing dealer out. Billing dealer in is basically the component that takes or consumes the records from the P gateway, and dealer out is the component that basically serves those records to the billing system. And these keys are distributed on a trust basis. So that means the KMS or the key management system is going to establish a bidirectional trust relationship with the dealers. And only after the trust is established, those keys are distributed in a secured way. And those keys are used basically to encrypt the messages or the records and store it. And the keys are also used to make sure those records are read correctly before handing it over to the billing system. Now, the most important aspect here is the key. The key is generated and distributed in a way that no human beings or no systems can ever come to know what that key is. The key is generated inside cryptographically, is distributed cryptographically, and it's used cryptographically. And it's always stays, and the key always stays inside the SGX the boundary. So there is no way that anyone can go and take a look at the records or tries to steal the key to tamper with those records. So that's just an overview of that. I have a talk on Friday in which I'm going to talk about the whole technology in detail, as well as some further extensions of protecting the data plane and the control plane using SGX. So if you guys are interested, please feel free to attend my talk. So what do we get from these components? Basically, we have a SGX based fully automated and distributed billing system, which protects your billing records and stores it securely. And we also have a way to make sure those records are not only secured, but they are also auditable. That means at any point of time, someone can challenge this SGX system to prove its authenticity, and there is a defined way. Again, the cryptographic way to prove that those components are running as intended and they have not been tampered with. You saw in the repository there are tools that will help you with the orchestration of these components, including provisioning and using it in environments like VM or Docker. Basically, that is critical for deployment and scalability. So with that, I'll quickly go over this. This is not important at this point, but just to give you an overview of SGX, basically Intel SGX is a technology using which you try to protect your application, and not just the whole application, certain aspects of the application, like let's say there's certain functions in your application that deals with encryption keys, passwords, credit cards, user information, whatever, right? Whatever secret or sensitive information you have, you can actually protect them inside an enclave, which we call the SGX enclave, basically. So today, when you deploy any applications in the cloud or in your data center, right? So the attack surface is basically your entire application. That means the application itself, if it goes bad, or some part of the application, if it's compromised, then it can go and basically steal all your secrets out. The operating system obviously has access to all the applications. It can go and look at the memory of each and every application and see what's going on. And the VMM is definitely more powerful. It not only has access to your VM, but it has access to pretty much all the VMs running on the VMM. So the attack surface today is huge. What SGX tries to do here is it reduces the attack surface. That means you don't have to trust your entire application. You don't have to trust your operating system or the VMM anymore, because they will not be able to look into those yellow boxes anymore. And you protect everything that you want inside those yellow boxes. You can also see there is a hardware, a certain section of the hardware that we have to trust, and that is the CPU. So you have to trust your application's enclave memory. That means the enclave code that is running inside the yellow box inside the application. That is, of course, that you have to trust that application, and you can establish the trust in a certain way. And on top of that, you have to trust the Intel CPU. And these are the only two things that you have to trust. You don't have to trust anything else to ensure that your secrets are not compromised. And the way the SGX system works is it works very similar to a library. That means if you have an application, typically your application links with certain libraries. SGX also works in the same way. You create a library that will be loaded inside an SGX enclave. You link to that library, and there's a certain way to call into that library. And if you take a look at Intel SGX, the tools, we provide the SDK for both Windows and Linux. And we also provide the GDB environment if you want to debug your enclave in some certain ways. So all these tools and development environment are available for SGX development. Okay, so now let's quickly look at some of the tests that we run in our backend, as well as some of the performance numbers that we have captured so far. So again, number one is we just talked about it. There are some VNFs that we have open sourced. The GitHub link is on the slide. Those VNFs can be, not all VNFs are must for your deployment. You can pick and choose whatever is required as per your application and requirement. We also have the the scalable and auditable SGX billing system. Uh, the way the billing system application has been designed is it is supposed to run on SGX enabled machines. So today we only have the Xeon E3s. Uh, their previous generation was Skylake. The latest generation that we have in the market today is called the Milo-based uh, E3s. Uh, those are single socket machines. They are perfectly okay to run the billing system. Then the way the application on those systems have been designed is that one SGX billing frame. When I say frame, it basically means all the three green boxes that I showed in the earlier slide. The one SGX billing frame can handle up to 7 data plane frames. That means it can collect data from up to 7 P gateways. This is the official characterization that we publish. Although internally we have tested, I think we've tested up to 11, but for stability purposes, we officially say the number 7. So because number 7, I think, based on all our tests and all our conditions that we have applied so far, we have seen 7 as the most stable number. So there is a 1:7 or 7:1 ratio between the billing frames and the P gateways. Now coming to the gateways, the packet gateway, the S gateway U and P gateway U, they follow a run to completion model. That means for uplink and downlink, for example, there will be a core that will collect the packets from an interface, process the packets, and then throw the packets out on the other interface. So that's one direction. Let's say that's uplink. Then there'll be another core which will be doing exactly the same thing for the downlink. That means collect it from the SGI interface, process it, and throw it out on the S1U. And there are 2 more cores required for various purposes like ARP handling, stats, and other interface between the S gateway U and C. So there's another code that's also responsible for the communication with the control plane. So overall, 4 cores used in the S gateway U, P gateway U configuration, and so far we have tested up to 2.5 million packets per second across 500K flows. That means we have simulated 500K flows, roughly equivalent to 500K UEs. And for 500K UEs on a single 4-core implementation, we have tested up to 2.5 Mbps. Now, one point to note here is this is another research topic, and I'm going to talk about this in more detail on Friday, is that nothing stops us from implementing a secured S gateway U, P gateway U using Intel SGX servers. And that's very much possible, and that's very much happening as we are talking today. The research is ongoing, and we are actively working on that. And the reason is very simple. The reason is based on the current trend of deploying this P gateway use. The control plane typically can be centralized, can be running in your data set. However, there is a trend where the P gateway use, or typically the MECs, as we call it, the mobile edge cores, the mobile edge cloud, or whatever we call it, those components, there's a trend that those components are being run close to, let's say, the RAN, or close to the customer where the data is generated. And typically the model is preferred because that model gives you a low latency versus getting everything, all the data plane traffic flowing through your data center. And when those gateways are run on the edge, maybe in a shopping mall or in a big place or a public place or in a big enterprise, there is a need for security, and at that point, security is no longer optional. So we are also working on making the S gateway, UP gateway implementations protected using Intel SGX. Okay, so last but not the least, the gateways are Linux aware. That means when the gateways run, although they are DPTK based, but because we have used the KNI interfaces, so the KNI interfaces are attached to the application. So typically, if you want to probe your application, see if your application is behaving the right way, you can always probe through those KNI interfaces. They appear as regular interfaces on the network, and full Linux capabilities are available on those interfaces. So all the ARP request responses, route tables, they can be all set up through those interfaces. All right. So coming to the test environment, we use one of these test generators. Again, Mikhail is going to talk about in detail what those really mean. But as far as the testing is concerned, we have tested it with 3 different type of generators: NG40, Polaris, and IL Traffic Gen. Each of them, they have a different performance profile. However, the number that doesn't change across these test generators are the number of UEs. We have tested that. We have tested those generators and our stack against 50,000 UEs. However, the rate at which those UEs are attached or detached, those change. For example, for NG40, we have a 1000 TPS profile. Polaris, we tested with a lower number. And with IL Traffic Gen, we tested with a higher number. Basically, for both transaction per second and packets per second, we tried to we followed a low, medium, and fast way of doing it. So you'll see some numbers which are at the lower end, then some numbers which are in the middle, and then some numbers basically which actually appear at the top. So that's the performance profiling numbers, what we have achieved. Now let's quickly take a look at what those config file options or the makefile options mean. Those are important. Starting with the first, which is the data plane SIMUCP. We have not used that, although our data plane is capable of simulating CP, where you don't even need a control plane. The data plane itself can simulate all the UEs, but that's not something we tested with. We made sure that we can also test our CP. So we always have a CP combination. That means a control plane data plane combination. And there are some tests where we didn't use the SIMUCP. That means the simulation in the CP. And for IL Traffic Gen, as I said earlier, it doesn't do control planes. So we used the control planes SIMUCP feature to test that. Static ARP Linux, the next two basically means do we want to use KNI or not? Static ARP means we don't use KNI. We have static ARP entries for the gateways. So we basically have a file called static-arp.cfg. You open the file and basically program the IP addresses and the MAC addresses. And our fast path will refer to that file. If there is a ARP request, it will formulate the response accordingly based on the information that's available in that file. So there is no KNI there. But if you don't want that behavior, you want full Linux behavior where the ARP requests and responses are being handled by the Linux kernel, sure, you can switch to KNI, which is the Linux mode. And we have we try to cover some tests with KNI, with some tests with static ARP to make sure the functionalities work across different traffic generators. Now the next two, that's also important. The communication between CP and DP, we have two ways to communicate. One is the UDP, where although there is technically there's no notion of a server in UDP, but for the sake of the connection, there's a DP that opens a UDP socket. The CP sends the UDP requests and gets responses back. So that's completely UDP based. But one important point here, to note here is the DP opens a socket. So it's still a socket that needs to be opened at the DP end if you want to communicate with DP using UDP. But you can also configure uh, uh, the DP to not do UDP and talk ZMQ or 0MQ based messages, basically. So the CP and DP in that case will not use UDP, it will use the ZMQ communication. And the good part about this is neither the CP nor the DP have to open any sockets. As we all know, the ZMQ works, the messaging system works in a different way. You can have a streamer in between where the control plane and data plane, they communicate. They actually connect to the streamer. So both CP and DP will connect to the streamer first, and then the communication from CP to DP or DP to CP can happen. And that's on TCP. Again, based on the configurations, we tried different combinations here to make sure all the options are exercised and tested. The last one, which is the FPC-based communication, we have not tested that at all. Okay, coming to S1 MME S11, straightforward. We have tested MME and S11 interfaces based on certain test generator patterns. Then going to the conformance, again, for some tests, we turned off SGX CDR, we turned on SGX CDR for some other test cases. And this table clearly tells you for what generator patterns we have enabled and for what we have disabled SGX. Then there are certain other tests like the sequence number test and the DP direct notification, DDN notifications. Those have not been tested yet. Again, when we say not tested, it doesn't mean the code is not present. The code, for some features, the code is present but may not be active or may not have been actively tested. So again, please, if you or your application requires any specific features which you see here but have not been tested, I'll strongly encourage you to simulate that environment and test our components. And if you find any issues or if you want to contribute, please feel free to become an OMEC contributor and submit your pull requests. Okay, I'll not go into too much detail into the environment. Basically, this is all our internal stuff. We tested with we tested it with the CPU cores, pinned CPU cores, non-pinned, just to make sure we see a performance difference there and accordingly suggest the configuration based on the performance numbers we see. And we also have a co-located bare metal setup where we don't have any VMs, but we just run the control plane, data plane, everything on a bare metal operating system. All right. So again, please go and look at the release notes for every component. It will tell you a lot of details what this component supports, what all configurations or specifications it has been tested against, and that will definitely give you a good understanding of what kind of test or what kind of applications you can run on them. All right. So with that, I will quickly show you a video of those components running. So you'll see those components running in action, and you'll also see how they interact, how they work. So let me stop sharing this presentation and switch to the video. Okay. Can you see my screen? All right. So what we have done is basically the entire flow that involves all these components that I just described. The entire flow with a certain test or a traffic generator, we captured the entire flow in a video. And this is the video I want to show you, and I'll also describe what we are looking at, all these components. So starting here on the right hand side top is so right now, whatever screen, the current screen we are looking at is the SGX billing system. And the top right corner is the SGX billing system router, which basically routes encrypted CDR messages from the dealer into the dealer out. Then we have the KMS on the top left, followed by the dealer in, dealer out, below the KMS. And on the right side, below the router, we have the CTF and CDF, which is the charge trigger function and the charge data function. So let me start playing the video. What we are trying to show here is, first we'll show how those components start, how they initialize and interact. So first what we do is we go and start the KMS, and we wait for the KMS to initialize. And when it initializes, it also shows a bunch of characterization features that you have to note if you want to deploy it in a production environment, and those are important for security. Okay, eventually we start the dealer in, and then we start the dealer out. They talk to the KMS and they exchange keys. They get their keys, and they are just now waiting for the messages to appear from the data plane. On the right hand side, we also initialize the charge trigger function, and you know what, let's quickly go back just to show you that. On the right hand side, we show the charge trigger function and charge data function being initialized. Again, as you remember, the data plane or packet gateway is going to interact with the dealer in, and the charge trigger function and data function, they're going to interact with dealer out. And the messages between the dealer in and dealer out, they're going to get routed through the SGX router. Okay, so now we'll switch to the other screen. In this screen, we have the control plane and the data plane shown on the boxes, the lower boxes. Sorry, some messages. Sorry. Okay, sorry about that. Okay, and so on the left hand side we have the control plane, the right hand side we have the data plane. We just started the data plane in the video, and then we'll go ahead and start the control plane. There you go. So the control plane has started, and the top panel is the load tester. That means we are using Polaris load tester here. And once we have the control plane data plane started, you can see we go to our next screen, which is the third screen, which has our HSS, the database, the MME application with all its interfaces running. So first we'll get started with the HSS. So the HSS service starts on the left side. On the right side, we'll start the MME. The MME, we start the main application, which shows the MME statistics, and then followed by the S1 interface, S11 interface daemons, as well as the S6A side, which will talk to the HSS. So once we start the S6 side, then we'll talk to the HSS and interact and exchange bunch of messages. Okay, so with that, now we have the system pretty much set up. So at this point, what we will do is we will run our traffic generator. And you can see we started the traffic generator on top. The traffic generator is going to first go and try to attach all the UVs. For this particular demo video, we use the configuration for 32,000 UVs. So the traffic generator is going to talk to the control plane and generate and send a request for 32,000 UEs. But on the other side, you can see the MME is fully active now because it's getting those messages from the traffic generator and it's provisioning those requests into the control plane. So right now you can see the control plane going on, and you can see the requests coming in from the MME to attach those UEs. Our billing system is silent because the UEs are still not fully provisioned, so the data traffic has not started yet. So you can see on the router, which is on the right hand side, only the initialization message has come, but there are no other charged records or messages being sent at this point because the data traffic has not been started. So the UEs are still getting attached. We are at 20,000 roughly. 20,000 UE has been attached so far. The attach rate is set at 250 per second. That means, and this is configurable based on whatever test you plan to run on your side. So this is going on fine. I can increase, I can change the speed. Let me go ahead a little bit more. There you go. So, okay, so now we are almost there, provisioning all the UEs. So, okay, all the UEs have been provisioned. Now the test generator, or the traffic generator is going to start the data plane traffic. At this point, we are doing some UDP traffic, both on uplink and downlink. And then you can see the traffic flowing, the traffic started flowing on the data plane, both on the uplink side as well as the downlink side. And it will tell you how many packets have been received by the interface, how many packets have been accepted for processing, how many packets have been sent out on the other side. And the statistics will be displayed for both uplink as well as downlink. So once the data packets have been sent and I think the data packets were sent for 30 seconds. And after the data packet sequence has ended, the test generator is going to again start the detach procedure. Now you can see the detach procedure has started, but you can also see on the SGX billing system, you can see messages have started coming in. So because the delete session requests have been successfully completed for UEs, those records, whatever the data that was exchanged between the UE and the application server, that data was accounted, was rationed, and based on the numbers, those records were generated. Those records are now being transferred to the SGX billing system, and you can see those records are being transmitted through the billing router. So those records are going to going through the SGX billing system. They're actually right now they're being stored securely on any file system. Doesn't matter. It can be local or remote. So as you can see here, as the delete sessions are happening, the records are being generated. They are being stored, but they're being stored in a way where more records are coming in. So they're still in the append mode. So records are being securely stored in the append mode. So as long as those records are still in append mode, the charge trigger function or the charge data function, they will not actually trigger. For their operation, for their processing, they need full stack. I mean, the full complete record. So they are still waiting. They don't see any full records that have appeared on the file system. So I'll take you through here. So at this point, you can see messages are still flowing, records are still being generated, still being saved, but they have not been put into a state where the charge trigger function or the control function can consume it. So it's still flowing, and so typically for every UE, there are two records sent. One is open record and one is a closed record. So for every UE, there are two records generated for 32,000 records. Sorry, for 32,000 UEs, you will see that 64,000 records have been generated in the billing system. So the test has completed. The test generator has given its verdict for all the 30,000 UEs attach and detach. The control plane below is showing 32,000 attach and detaches. So that confirms the data that's shown by the test generator. And the data plane is showing the number of packets that flowed between the downlink and uplink during the test. Okay, so the MME is also showing the same numbers on top. Otherwise, it has gone silent because no more transactions are happening on that side. We stop the control plane, we stop the data plane. And then we switch to the billing system. And now you can see the charge trigger function and charge data function, they got triggered because the complete record is available for processing. And it has detected that, and it connected to the SGX dealer route. It has to prove itself. So that means it has to have the right certificate with itself to be able to prove its own authenticity over the SSL channel. And only once the SGX enclave, which is the dealer route, verifies the authenticity of the charge trigger function and data function, will it send those records to those components for processing. Okay, so with that, that was all in the demo. So now what I'll do is, so you can ask questions at this point, but I would say you hold on to your questions, and let's quickly jump to the next session, which Mikhail will give us based on the CI/CD setup and process using which you can actually contribute to OMEC. So once he's done, then we can take questions in one shot.